Okay, thanks. Yeah, so that's project that I'm working on with Mattia, Talpo, and Richard Thomas for maybe 3 years, or maybe even almost 4 years. And the question we were trying to answer, well, the initial impetus was to do a logarithmic Donaldson-Thomas theory. But the question behind all this is, what is a good refinement of coherent sheaves in log geometry? So there is a log geometry deals with situations where you essentially two basic cases, I think. One is when you have a normal crossings divisor, so that's a situation of a pair x comma d, and the other is when you have a degeneration and you look essentially at the total space and maybe restrict to the central fiber. So it's a degeneration situation, and log geometry would immediately generalize this to situations where rather than just the normal crossings divisor, you have a toroidal pair, so that the pair x comma d locally looks like a toric variety and its toric divisor. And then these would be called log smooth situations. So these are, whenever this term comes up, you should think, well, essentially toric. Okay, but with a twist. So meaning it looks like a base change of something toric. Now, when I say good refinement of coherent sheaves, of course, log geometry is some additional data to an ordinary scheme, so you can talk of ordinary coherent sheaves. But the coherent sheaves don't talk to the log geometry. And it has been a question that I don't think still has a good answer in how to best couple the coherent sheaves to the log geometry. So why do we care? I mean, applications are obviously, if you want to do something like logarithmic Donaldson-Thomas or Pandari-Thomas theory for pairs and toric degenerations, just for computational issues, you want gluing formula that help you in computing these things. You could also think of, and that's a big topic classically, at degenerations of moduli spaces of sheaves. So there's a huge body of literature already for line bundles on curves, and vector bundles on curves, and goes on. And of course, once you have a good theory, you could then use this language of log geometry to study these. There's also a case that has been used. If you look at one famous class of hyperkähler manifolds, or the Hilbert schemes of points on a K3 surface, and these are complicated spaces, and they're very nice log smooth degenerations of K3 surfaces, a classical theory. And once you have a good theory of log coherent sheaves, you can talk about something like the Hilbert scheme of points in the induced degenerations of the hyperkähler in terms of the Hilbert schemes of points on the K3 surface. And then, even if you don't care about enumerative geometry or these moduli spaces, you could just try to construct bundles, let's say on a Calabi-Yau threefold, by deformations from a singular situation. So you would look at something like this, the x0. Let's say you have some method to produce bundles on that guy, and then you want to enrich it with some logarithmic structure, and maybe that you can also do, and then you have a better chance to produce something on by deformation theory on the total space. And one fantasy maybe is also to look at stability conditions and construct stability conditions or investigate stability conditions near kind of large degeneration limits. Okay, so I think enough motivation. And there are a bunch of candidates for these coherent sheaves in log geometry. One has been done by Born, Vistoli, and Talpo has also done some work on this. It's called parabolic sheaves. And they really come from these parabolic bundles that are classically known on curves, where you have some kind of flag at a point. These can be conveniently just be rephrased, let's say, in a situation where we have a pair x comma d, normal crossings pair. There's an infinite root stack associated to such a pair. simply by taking branch covers over this abelian branch covers over this divisor. This branch rule is a divisor, and dividing out the Galois group of the cover, and that gives you, taking the co-limit of this construction gives you the infinite root stack, and you could just look at bundles on these things or coherent sheaves, and these are these parabolic sheaves. Then there's this expanded degeneration point of view of introduced by first in symplectic geometry and then by Jun Lee in in Gromov-Witten theory, of relative Gromov-Witten theory, and then for quad scheme by Jun Lee and his student Baoshun Wu, in the case that the divisor of a pair x, D and D is a smooth divisor. And more recently, Malik and Ranganathan have done actually built a theory of logarithmic Donaldson-Thomas theory based on sheaves with one-dimensional support that are transfers on these expanded degenerations. So an expanded degeneration is just something where you replace your space with a deformation to the normal cone. So then you don't have just the pair x, D, but you put it takes a sum with fibered sum with fibered co-product with certain projective bundles over D. Then there was a very tempting approach that I will say a few words on it, that we actually followed we spent a lot of time on that, probably 3 years or so, thinking that this should work. Looking at a module of an OX algebra that is naturally associated to a logarithmic scheme that I'm writing as OX log. And it's tempting to look at these modules. I'll say a few more words on these, but it doesn't appear to work very well. And then one can look at sheaves on closed Lux subschemes, which is actually closely related to this expanded degeneration point of view, and that's the point of view we have been following since about beginning of last year, and we learned at the beginning of this year that Patrick Kennedy Hunt, student of Dhruv Ranganathan, actually has a paper almost finished his thesis work that is very, very close to this point of view. And in this talk, I'll restrict to just the log-Hilbert scheme, not the quad scheme. Okay, so before continuing with the talk, I feel compelled I should say something about logarithmic geometry, and I won't give the kind of monoid sheaf version of it, but something that is very natural for what is coming. This is this approach via stacks due to Martin Olsen. So how does this go? So you start with a rational polyhedral cone, and then you can define the corresponding affine toric variety. This has a torus action, and it takes a stack equation. Okay, so that's a zero-dimensional Artin stack. And so let's just do it as one example so you get some feeling for what this is. It's a really weird space. So you take, let's say, A2 and divide out the torus, the two-dimensional torus. What you get is essentially 4 points, okay? So here this closed point, oops, I erased it. This closed point, of course, is just a point mod GM squared that gives a BGM squared, okay? On each of these strata, you have one direction that you can just divide out, and then you are left with the GM quotient of a point, so that gives 2 copies of BGM. And then this one open stratum is a point, okay? But this is just spec K, okay? But this point is actually open. Oops. Well, this is a closed point over here, okay? This is a closed point, that's an open point. So and then with this language established, a log structure on X is just given by a morphism from X to a stack that you glue from all these local models. So what do I mean by this is co-limit. So whenever you take another cone that sigma that is a phase of the another sigma. So let's say the one corresponding to this stratum, that gives you an open embedding. Okay, so this BGM in here is an open subset of this BGM squared. Sorry, of the whole thing, and then you can take takes a co-limit of these. So this gives a big stack, and it classifies log structures. That was Martin Olson's insight or point of view. And then you can just say a log structure on X. Oops, sorry, that slipped here. A log structure on X is simply a morphism to this stack. Okay, from this point of view, it's very natural to see you see each point here goes to some sigma and some minimal sigma, and that minimal sigma is give you a stratification on X. So there's some logarithmic strata on X, and they are just pulled back from the strata of these toric varieties or the corresponding quotients. Okay, so they're decorated by these cones sigma. Then if you have all these cones, you also see that whenever you go to a bigger stratum, you get a phase map, okay? So this guy, then you can take the co-limit of all these cones, and that gives a cone complex, a complex of rational polyhedral cones that we call the tropicalization. And it's really closely connected to what is traditionally seen as a tropicalization of let's say a hypersurface and so on. Okay, so let's do a few examples before moving on to see a little of the features of this kind of abstract log geometry. If you're maybe more used to thinking of pairs, if you're thinking of pairs, you never need any of this fancy machinery. You can just express everything in terms of line bundles. But here you could, for example, talk about log points. Okay, so there is simply a morphism from spec K to A sigma. To some A sigma, okay? And of course, you can choose this sigma minimal. So for example, in this A2 thing here, there's some interesting log point at this point is just given by this morphism to BGM squared. So it looks like spec K, but it has some additional structure coming from this morphism to the Ardian stack. Similarly, if you have a simple normal crossings divisor in a smooth variety X, you get locally these models, eta locally, you get a model, a morphism to AR. That is a quotient to this thing that I would have to write curly A, and then that takes a quadrant, or the octant, the R-dimensional octant. And while these don't patch, okay, these things don't patch, these morphisms from you to this guy, they patch. So you would get a morphism from here to this stack. And that would be the same as giving you this simple normal crossing structure. Then what is also nice to see from this point of view is if you have a log structure on some scheme X and a morphism Y to X, you immediately get a log structure on Y simply by composing these morphisms. Okay, so that's a pullback log structure. And actually, this log structure from log point is pulled back from taking the inclusion of spec K in A sigma, okay, as a closed point. So this is induced from here. If you take the pullback log structure for this inclusion, that's exactly the log point. So, and then something very cool, very important for us is that you have a notion of log modification. This goes as follows. So you look at locally, the log structure is given by a morphism to this Ardian stack A sigma given by one cone. So think of sigma, you see there was a dualization in my definition, okay? So this sigma is really the fan sigma. And everybody who has ever worked with toric geometry knows that subdividing such a sigma provides a toric modification. So it's a birational toric morphism from something I call, well, I didn't write it here, but there's a toric variety up here mapping to the A sigma. So maybe I should write it, I could write it over here, right? So maybe there's a toric variety, let me write it just TV of sigma, and that goes to A sigma. And then I take the quotient by the tori, and I get these maps, these spaces. So, and then you're saying a log modification is locally given by a Cartesian diagram like this. So it's a morphism of log schemes, x twiddled to x, such that locally such a diagram, it fits into a Cartesian diagram of this form. Now this has a strange feature, right? So if you start down here with something that looks like a pair, okay, a toric variety, then you just retrieve the ordinary toric modifications. So just blowing up toric strata and stuff. But you could start with, say, a log point and do the thing, and what you get is a fiber of that toric modification over that point. So you could start with a spec k here and obtain up here an exceptional divisor. Okay, so that can also be a log modification. So log modifications need not be birational. Okay, but they are locally base changes of toric birational morphisms. Okay, so then I promised to tell you something about this failed approach. You know, we always talk about things that work. I think it's sometimes good to.
Bernd,
sorry?
Before you do, can I ask a question about the approach that you just took? Sorry,
Yep.
the picture.
Yep.
So, am I right in thinking? Okay, so x, there's a log structure on x is a morphism from x to this limit.
Yep.
And I think under reasonable conditions on x, that it'll actually only hit a finite part of that limit. Is that right?
Right. Right.
So is the log structure on x something like somehow it's some map to a toric variety, or what, how do you can you unwind this into more classical terms? It's lovely. I just wondered whether.
Well, yeah. I mean, if you unravel this definition, sure, you would have like locally you would have a morphism to a toric variety. That's correct. Eta locally, I should say. Eta locally, you have a morphism to a toric variety. So you would have these kind of what I call charts, you know, something like this. And then when you change to a different chart, the sigma can change. So you would have a common subset, and then you can also change by kind of maps from your U to the toric automorphism group. Okay, so that's all there is. So these are the local models. So you could equally well define log structures in terms of charts, and then you glue the charts in terms of these morphisms that don't change the morphism to the Stecky quotient.
Right, I see, but somehow mess with the toric structure so you don't end up with any kind of...
Yeah, it's not, so that's exactly the point, right? So any normal crossing things would be a log smooth variety, but of course they are not all toric, right?
Thanks, that was really helpful.
Okay. Okay, so let's continue. Yeah, please feel free to interrupt me. To be honest, I hate these Zoom talks. It's just because it's so, I mean, it's like, it's a very autistic experience. I'm just sitting in front of a screen and talking to myself. So please interrupt me if you feel like it. I appreciate it. Okay, so yeah, so we always, I was just saying, we always talk about like things that work. Okay, so if younger people are listening, and are still struggling with things that don't work and are angry with yourself, well, most things don't work. So here's one thing that didn't work, and I spent a lot of energy on it. It didn't work so far. Who knows? I might have at some point some better idea. So we wanted to consider ideals in the log structure sheet. So what I haven't told you is that and now I'm compelled to say this. I have to say this. There's a sheaf of monoids associated to it. So that's the original definition of a log structure. So how does this come about? The mx, if you have a toric variety, the mx would be just you take the invertible functions on the complement. Maybe I should write a sigma here. Okay. So you have an a sigma, that's a toric variety. You take the invertible functions on the complement of the toric divisor that extend to regular functions. Yeah. So that means you take all the regular functions that have zeros at most along d sigma, your toric divisor. So that's obviously a subsheaf of OA sigma. But it's not a homomorphism of abelian sheaves, or that's not abelian, right? Well, it's an abelian sheaf under multiplication, but it's not no, it's not even abelian, right? So it's a monoid. You can multiply, right? And it's a homomorphism of sheets of monoids. So anyway, so we have this weird sheaf MX and a morphism to OX, and in here you have the invertible functions, and they pull back to a copy of the invertible function, so that is sitting inside MX, and that's actually a condition for defining log structures. So a log structure would be a sheaf of homomorphism of sheaf of monoids, such that the pre-image of the invertible functions map isomorphically to invertible functions. Okay, so we have this weird sheaf, and we can turn it into an OX algebra, OX of MX. Then that is a big thing, and especially what is especially big is because in MX you have this copy of OX star, so you kind of overcount, right? So OX star appears twice, first as this copy in here and then in here. So why not dividing it out? And that's what you do. So you divide out, pose the equivalence relation that if you multiply a z to m, which would be the notation of some element in here, yeah, the toric notation, by some invertible function, you want it to be the same as z to h times m, okay? So the problem with this is that this whole thing has just too many ideals to be useful without any further conditions. So you just play around with the notion a little bit, you realize it has no chance to be finite type or whatever. It's just humongous. But with a little effort, you can identify conditions on your ideal sheaf stockwise that actually make it look pretty reasonable, and actually parameterize exactly the situations that we will have in the end, namely a closed subscheme of a toric blowing up of a product of x with of x. Okay. So there's a notion of logarithmic ideal sheaves in this weird sheaf of OX algebras that parameterize pointwise these kind of situations. So where you take a toric blowing up of your target, like I explained before, and take a closed subscheme in there. But we tried very hard to turn this into a global theory, and somehow this just doesn't behave very well. Any notion you cook up never behaves very well under generalization, and it doesn't seem to be a good theory. So we tossed this into the wastebasket and said, if we end up with these situations, then why not embracing that thing? So, and that led to the theory of these log Hilbert scheme based on closed log subschemes. So that's another curious thing, that if you look in what is the only book monograph really available on log geometry, this wonderful book by Arthur Ogas, there's no notion really of a closed log embedding and the closed log subschemes. There's only a notion of strict closed log subscheme, but no such notion here. Although something more was known to some people, I guess. Anyway, so let me, for simplicity, not work in the relative situation. Let's just work absolutely. And so we have to define a notion. What is a closed log embedding first? Okay. So what I do is one crucial difference to the ordinary situation is that because log points can have structure, it is relative from the outset. So of course you can just define what should be a closed log embedding for x, but that will be immediately too restrictive, as you know. It has no chance to give you a proper modelized space, or not even a subspace in there being proper. So what you have to do instead is take a product of X with any base scheme S, okay? And then look at diagrams like this. So you have a morphism from a log scheme Z to this product XS, and you impose two conditions. Maybe the second is really the one that gives a closed log embedding. Namely, we want that F factors over a strict closed embedding, this notion that is in Oge's book, after a log modification of your target. Okay, so you would have the XS tilde is up here locally, and then you want this kind of thing to be strict. And the second, so what does strict mean? Strict just means that the morphism, that the log structure is defined by pulling back from XS tilde, okay? So this is just what it means to be strict. So it's essentially a non-logarithmic if you want, right? So if you know the map, you know the log structure. So there's log modification, you have a normal closed embedding, you just pull back the log structure. Of course, that can be silly. And what you want is some kind of notion of transversality, and that's done by the technical notion of log flatness. So you want this morphism, not this one to be log flat. So Z should be log flat over S. I'll unravel this a little bit, so you see that what it has to do with toric transversality. Okay, so I explained this, right? It's a relative notion, even if S is a point, you know. And I had explained before what a log modification is, and just reminding you here what it meant. So let me explain log flatness a little bit, and then we go back and I ask for questions. So log flatness is a notion of flatness in log geometry due to Kato, this work of Olsen, Gillum, Oges, Tevelev, probably many others. So what's the definition? Well, there are many equivalent definitions. Let me give you one that I find most geometric. So let's just look at a log point. Actually, it's open. So if I tell you what it is over log point, then you're good. Over log point, it looks like this. Okay, so you have this local model of a morphism Z to spec Q to K. So that guy has that morphism here to this toric variety AQ is a chart for the log structure. And up here, I have a chart for the log, a chart for the log structure of this log point. Up here, I have a chart for the log structure on Z. And then whenever you have such a morphism, locally, there will be such a diagram. Okay, you can find charts such that this fits into such a diagram. And whenever you have such a diagram, then this F here is log flat, if and only if, well, not the map from Z to the fiber is flat, but ordinary flat, but you need to adjust it by the difference in kind of tori that lurk around. Okay, so there is a lack of dimension that you can sometimes have, which is irrelevant because it's made up for by the rank of P being larger than the rank of Q. So you would have a morphism from Z, a torus action on two maps from Z to pi inverse 0, and this relative torus acting on this toric morphism, and you want that map to be flat. Okay, so let's do two examples so you get some idea of what that means. Let's take this to be 0. Then when is such a morph? Then we are just asking this guy to sorry, this is wrong. I mean Z to over spec Z over K is log flat, right? That means that so Z is absolutely log flat if and only if the morphism from Z crosses torus to the toric variety is flat. Okay, so we have, let's say, a subvariety of a toric variety. When would it be torically transverse? You let the torus act on this on the embedding and look at the map to the toric variety and ask for flatness. And that is actually Tevele's notion of toric transversality. Okay, so log flatness in the absolute situation with toric target just means toric transversality, and in general it can be over log point. It's just toric transversality. But note, I mean, it's z over k, but it involves a p, right? Because this is lurking in the log structure on z. And then there's a slightly more classical situation of Wu and Li with the expanded degenerations for logs for a smooth divisor. In this case, you have a simple, so in this case, the p is just a copy of n, q would be 0, so we are still in a pair situation. And then you can give this Tor definition. So if you like Tors, that might speak to you. So it's just telling you that multiplication by the defining equation of D is injective. Okay, so I promised, so and then there's two more. And then we go back and ask for questions. Let's look at this thing. So you can take an embedding of the affine line into A2, just a diagonal embedding. So this thing here, right? So it just takes a diagonal embedding as written below. And you pull back the log structure. So that gives you an n squared at the origin, at this origin for the log structure on Z. And you find that this is not log flat, right? Because this morphism that you write down here, this is not a flat morphism. It has a high dimensional fiber over the origin. Okay, so it's the line through the origin, you kind of just turn. Well, obviously, this has a two-dimensional fiber over the origin. That's not right. Other fibers are one-dimensional. Okay, so this is not log flat over K. So that thing would also not be a closed log embedding according to our definition. How can we turn this into something log flat? Well, rather than putting an n squared at the origin here, which comes from pulling back the log structure on the target, I just take the toric log structure that you see on Z. Okay, so that just gives you an n. And then I take the same morphism, okay? And that can be turned into only in one way, into a log morphism. So it would not be a strict morphism anymore, but now it is log flat because it's the map from A1 cross GM to A1. And this is log flat, okay? Whoops, there's some typo here. And actually, this is a closed log embedding because you can pull back the whole situation. So you can factor this morphism that I wrote down, this F, which is down here, over the blow up of the origin of A2. And if you do that, you get a kind of nicely transverse thing, right? This is obviously this kind of transverse situation that Tevelov is talking about. So this guy, and then this morphism becomes strict. So this would be a situation where you can see from what we had before here, this kind of factorization into a strict morphism and a log modification. So this thing is actually a closed log embedding, this morphism. Okay, so and then I promise to stop and give other questions here. We all have some rough idea of what these closed log embeddings do.
Do you have a question or not? Oh, no.
No, I was just conveying enthusiasm.
Okay, very good.
So there are no questions in the chat for now. So yeah.
Okay, good. Okay, so and then I said, well, just recall closed subschemes are an equivalence class of closed embeddings, right? So you have to look at such diagrams. We all know that. So similarly, we need an equivalence of closed log subschemes. So I have a morphism here, but a morphism that is kind of a log modification of the guy would still gives the same thing. If it's, yeah, it would still gives the same thing. So you could change your domain by log modification simply because that could arise from a log modification of the target. Yeah, so you could a log modification of the target, and then you divide out this this equivalence relation. Okay, and then you notice that this, what we have been doing, maybe on some other grounds, is actually natural also from thinking categorically and trying to understand what is a proper monomorphism. Okay, so in scheme theory, a proper monomorphism is indeed a closed embedding, and one can show that Z to X is a proper monomorphism in our as a morphism of log schemes. To be precise, you have to work in F as log schemes, if that phrase talks to some people in the audience. If and only if there exists an FS Cartesian diagram of this form, and that's exactly what we did. Okay, so up to this kind of log modification, we have a strict closed embedding factors over log modification. Okay, let me say this again. The proper monomorphism of FS log schemes is the same as saying there exists a log modification such that after pulling back, it factors over strict closed embedding. Okay, so that's our notion. And once you have this notion, it's not hard to cook up the corresponding stack of closed log subschemes. Well, it might be slightly annoying that you have all these log modifications, but whenever you have a log modification and you look at all these strict closed embeddings, that gives you a chart. That gives you some open neighborhood of one strict closed embedding, of one closed log subscheme, and hence there is an algebraic stack that you just take as a co-limit of all the things that are kind of given by Hilbert schemes of closed subschemes in log modifications.
Could you say exactly that again?
Okay, so you take, when you have a transverse subscheme, okay, then you can look at a neighborhood. You can deform this closed subscheme inside that target, keeping transversality. Okay, so for example, we had, let's say, this thing, right, and then if this is your Z, you can move it like here. It will always stay transverse. So that would be an open subset. And then, but now you allow your target to vary by taking log blowups, log modifications. But that will, once you have something transverse, there's a unique pullback is a nice pullback, and it stays transverse on any further modifications. So that's why this is an open embedding. Does this make sense?
Yes, thanks.
Okay. But of course, that's not the space we want, right? I mean, this is far too big, right? It's non-separated. It's far from finite type, even after we fix the Hilbert polynomial and so on. And this finite type problem and the non-separatedness, both are actually common log moduli problems. And there's a fundamental reason for that. Any of these log objects that you want to parameterize depend on the choice of a log structure on the base. And let's say we have a log object over a log point. We can always crank up the rank of this monoid in some stupid way, right? So just add on some powers of n to l, powers of n, and then there's a log morphism like this. You pull back. So why would that gives you another one, right? So there's no reason. It's obviously not of finite type, and it's very bad. And in our specific situation, there's some other reason which has to do with the fact that we do log modifications. But let me maybe not expand on that. And the reason why log moduli problems are problematic is well known, right? And I'll show you what you really need to do is you need to understand how your log geometry talks to your moduli problem. Okay, so the log geometry should be something that kind of is naturally rigidified by your moduli problem. And that is really the art of finding good log moduli problems, log moduli spaces. So the key question in our case is, we need local tropical moduli. So let me first explain this in a simple situation where everybody knows the answer, or everybody has ever thought more deeply about it, knows the answer. And that's hypersurfaces, okay? So if you look at tropical hypersurfaces, like plane curves or some other higher dimensional things, yeah, so what is this? A tropical hypersurface in a cone is a support of a balanced rational polyhedral complex. So it's a polyhedral complex consisting of rational polyhedra, and the balancing condition tells you there are weights associated to the polyhedra such that a zero tension condition is fulfilled in codimension one. And also there's a natural kind of polyhedral structure on any of these tropical hypersurfaces. They just look like these codimension one things that I'm sure you have seen, certainly for cases, for curves. And what you can do here is the task is to parameterize all such gamma, so all such tropical hypersurfaces in this case of a fixed degree, or maybe, yeah, of a fixed degree, maybe not bounded degree. No, actually of bounded degree by one polyhedral complex. So in particular, you want to define, you want to put together various tropical objects that look the same, okay? They have the same shape. They should be parameterized by a cone. So that's what I mean by parameterized by a polyhedral complex. So that by saying this, I mean there should be polyhedra or cones maybe, and in the interior of a cone, your shape of the tropical object shouldn't change. Let me do this in one example. So let's look at this conic, xy plus t2ax plus t2by plus t2c. It's a family of conics depending on these powers a, b, c. And depending on how you choose the a, b, and c, let's think of them as natural numbers, or maybe you want to do Puiseux series or something and think of them as rational numbers. Depending on how you choose them, you get different tropical objects. You get different decompositions of the Newton polyhedron, and accordingly dual to it these tropical curves. So if a plus b is c, you get this kind of thing that looks like a union of two lines, transfers to each other. And then if a plus b is less than c, you develop this vertex develops an edge. And if a plus b is larger than c, it also develops an edge, but in the other direction. So this means it's a polyhedral complex that consists of two cones, okay? This gives a cone, a plus b less than c, let's say real number, positive, non-negative real numbers, a, b, c, with this fulfilling this inequality. This is another cone, and they intersect in this cone, in a two-dimensional cone. They are three-dimensional, and they intersect in a two-dimensional cone. Okay? So whenever you have such a thing, you can hope for a good log moduli problem. Now, thinking about this for higher codimension, and when we have mixed dimensions, so we are talking about the Hilbert scheme, right? So no restrictions on dimensions or embedded components and so on. We need to define a notion of type of tropical subspaces in some cone, let's say, just to solve the problem locally, such that whenever two such gammas have the same type, we can form a sum. So there's some kind of cone structure, a monoid structure on the set of such tropical subspaces of the same type. Now, here are the two examples that you can play with that typically refute all naive ideas you might have at first. Just take 2 points, okay? So you want to add kind of define an additive structure on the set of 2 points. So if they are like this or like this, and you add them, you see, if you do it naively, I mean, how do you add? I mean, to add, I would say I take this point and another point, and I have to say one of the two pairs of 2 points I have to add. But then you can kind of form a one-parameter family, kind of swapping the positions of these 2 points. Then what was the first point and what was the second point? So how can you define an addition if you don't know which point is which? Okay. So, and the other one is two skew lines, right? So if you look at these two lines, and this one is parallel to that coordinate axis, that one is parallel to that coordinate axis, you see there is some kind of situation where they lie in one plane, and then they develop here a point that you don't see neither here nor here. So something is wrong if you want to kind of define a good cone structure. Okay, so let me explain a little more how this is done in more familiar situations. So the two cases I want to remind you of or explain. One is stable curves, and the other is stable maps that you use in log Gromov-Witten theory. So for stable curves, we all know we have this nice, proper, smooth Deligne-Mumford stack, MG. Maybe you want to write it as MG bar. I don't know. So I mean the Deligne-Mumford stack of stable curves, nodal curves. And in there is a divisor, a normal crossings divisor in the stacky sense of nodal curves, DG. Okay, co-dimension 1. Now, this is a situation, well, it's slightly stacky, it's an orbifold, okay, but still everything I've said before about log structures work on these stacks as well. And there's a log structure corresponding to this kind of normal crossings divisor, okay? So let me call this curly M. This is the log structure. The stock of the log structure at this kind of monoid sheaf at a point, or the kind of minimal monoids that we had before for these normal crossings log structures, they measure how many nodes you have. So let me draw this in this diagram. Let's say we have a two-nodal curve. Then we all know that the moduli space, that the versal deformation of this is a product of a smooth factor that takes care of hyogenes or something, or some other moduli you might have with marked point. We don't have marked points. And then the two smoothing parameters of the nodes. So this is a diagram which just records the two smoothing parameters of the nodes. So on one axis, one of the two nodes gets smoothed, maybe this one, and on the other gets smoothed. Okay, so you see that this talks nicely to your log geometry by the following fact. Whenever you have some technical terms that you may choose to ignore, log smooth, integral, vertical, log structure on a family of curves, okay, which would then automatically by this thing be and that one be a family of nodal curves, is a unique pullback in the log sense of the universal family. You know, so here we have a universal family. Sorry, this is this guy, which is also a log normal crossings pair. Hence comes with a log structure, and it fits into a log Cartesian diagram of this form. Okay, and what you find is there is a basic monoid. This is a monoid on the moduli space that you find, and this is just this N to L. So by looking at your curve, you can tell what your log structure should be. So what I said before with these kind of ugly base changes, this kind of thing, right? Sure, that can happen here, but there's a minimal choice on this side where I just take an N to L here. In this case, okay? And you can't crank up the L because it's just the number of nodes. This is the minimal choice. So it's minimal also in the sense of stacks. It's a minimal substack. Any other kind of comes by pullback. Okay. So then I could explain how this is related to tropical geometry in terms of metric graphs, but maybe I'll do this in the slightly to a situation which is slightly closer to what we are talking about. Maybe stable log maps. So if you have a stable log map, so that means you have a nodal curve. Let's say we work over log point, okay? Together with a morphism to your target, and then you tropicalize this. That gives a diagram of cone complexes. Well, this down here is really not a cone complex because we have a log point. It's just one cone. And then over this, you have a cone complex. But the fiber over each point here is just a metric graph. So the fiber here, so sorry, maybe over here, you have fibers are metric graphs. So you should think of this thing here as a family of tropical curves parameterized by a cone. Okay, so it's just a graph, and you vary the length of the edges. And then it has a morphism of cone complexes to this tropicalization of the target. Now, the basic monad, this kind of thing we are so eager to find, right? This minimal one, in this case, has this beautiful description. You look at the moduli space, so you forget about this situation, okay? And just look at this moduli space, a moduli space of tropical stable maps. And each of these come with a modulus, right? Just by varying the edge length and changing this morphism in a way compatible with all the directions. So that becomes naturally a cone. And you take these tropical stable maps of the same type, that gives a monoid, and you dualize. And that is your basic monad. Remember, tropicalization is always kind of dual, right? It sits on the fan side. We want monomials, so you have to dualize. Let's do this in one example, okay? So the tropicalization of X I explained before, right? We use this tropicalization. Let's take a conic in P2. There are many diagrams you can write down. There's a whole moduli space with many strata. I'm just writing down one stratum. So this is certainly something you can produce. I can produce for you very explicitly in terms of a generating family of conics. So you would have five vertices, which means 5 irreducible components. This is a fan of P2, and they map as given in terms of embedding into this is this map, right? So the blue stuff is a gamma, rather one fiber, right? One fiber of this map, and the orange stuff is the trop X. So in this case, you immediately see if you vary your tropical stable maps of the same type. What's the same type? Well, what can you do to this thing, right? You can vary essentially this length and that length and that length, and they can vary them independently. And that would not destroy the type, I mean, the shape of that figure. And indeed, that's a tropical moduli space, okay? So this QR dual is this R3 larger or equal 0. Then you dualize, take integral points. That was indicated here. I didn't say it. And that gives you an NQ. And that is the basic monad in this case, okay? So now we want to do the same thing or something similar for log Hill. And our proposal is to use hyperplane arrangements to do that. So this is just, I have to speed up slightly, I think, 5 minutes left. So we have this family, we have a closed log embedding over here. We tropicalize, we get a family of tropical subspaces, okay? So nothing wrong with that, looks all good. But the problem is that the poly decomposition of this gamma S that we get changes under the equivalence of log embeddings. And that's a big headache. Because once I have a poly decomposition, I can easily talk about type, very similar to what we did before, okay? But if the poly decomposition depends on your choice of representative of the equivalence class, you're screwed, because it will give different basic monads. Okay, but locally in X, you get these diagrams, okay? You get gamma as the support of a balanced polyhedral complex, whereas the polyhedral structure is not uniquely given, okay? So that depends on the choice. Now, what we define for these kind of things that look like support of a polyhedral complex, but which do not necessarily have a given polyhedral structure, is I can still define something that we call flats, which might be a slightly bad notation for people working with hyperplane arrangements. So we may still want to change this this term. But a flat in our case is just something that you would do naturally. So you just, this could look like this, right? So you have some polyhedral decomposition, and it fits into a flat part. So this whole thing would be one flat. So you just kind of extend as far as possible without having a kink. And then whenever you have a flat, you can write down various hyperplanes. Namely, first you extend linearly. Okay, so this is just the affine subspace, but it may not be a hyperplane yet. And then you can crank up dimension by taking a phase of your sigma. So tau is a phase. So the whole thing lives, your flat lives in sigma. Okay, we are locally in X, so we live in some sigma, and then we can take a phase and crank up the dimension by taking the tangent space of the phase. So that gives a bunch of hyperplanes associated to your tropical subspace, and you get a hyperplane arrangement. Okay. And then what you have to show is that indeed now each flat, sorry, the hyperplane arrangement defines a polyhedral decomposition, just the obvious one you would think of, right? You subdivide your space with hyperplanes, it has a polyhedral decomposition. And then you prove that each of the flats that we had is a union of cells of this polyhedral decomposition. Okay, so whenever you have boundary here, there will be some other hyperplane coming from some other direction, intersecting it and cutting out this edge. And that is not true for all polyhedral complexes. You need balanced polyhedral complexes. Okay, and then once you have this, it's easy to find a type. Namely, first at each point of X, you get a hyperplane arrangement, an associated polyhedral decomposition, and then the type of your tropical subspace is, well, you need to select the cells of the polyhedral decomposition that are involved. We don't just want the cells, I just want the category of cells. So the combinatorial kind of thing. So you have an object for each cell and a morphism whenever one is the boundary of the other. And then we need some notion of direction that tells you that kind of gives this kind of tropical behavior. Just as we had for the curves here, right? We don't want to change this kind of star of that vertex. Okay, so you would fix that star to define the type. Okay, and then of course you need the ones that cover the cells that cover this this tropical subspace. So let's do an example here. Okay, so we had this example of a tropical stable map before, and what is the kind of hyperplanar arrangement I get? Well, at each vertex I have to, well, first I have to extend these things. Okay, each edge gets extended. These give these kind of diagrams. But then we also have to extend each vertex in a way that cranks up the dimension correctly. So if I get this one, that we already had, but and that we already had too. But here we didn't have that one, and here we didn't have that one. Okay, so this gives two additional hyperplanes, and depending on how they vary, they may change type. Okay. So let's just move this slightly above, make this length a little longer so that these two lines agree and you get a different type. That is a different type. On this side, you would have the same type in log Gromov-Witten theory, but you get a different type in this kind of logarithmic Hilbert scheme that we are proposing. And then you need, the key lemma is the tropical subspaces of the same type can be added. So we get a rational polyhedral cone. that this addition is compatible with generalization maps. So you can actually glue this together. Will give a good moduli problem. Will be an open, that this basicness that we define as an open property in this big algebraic stack that we defined. Where was it? Where is it? Not here. Here. Okay, that was this one. This was log help tilde. So this is an open property, and that will be your good subspace. Okay, that should be Deligne Mumford, and so then of course you can tropicalize this Hilbert scheme, and that gives a notion of tropical Hilbert scheme based on hyperplane arrangements. That might be one point of view, might be interesting to explore further. Okay, that was my last slide, and stopping here.